Welcome. Today we're going to explore a really foundational concept in artificial intelligence, the problem-solving agent. We'll look at how these agents go way beyond just simple reflexes. Instead, they actually formulate goals, they plan out sequences of actions, and they discover solutions to pretty complex challenges. This is truly a core building block for any rational, goal-driven AI.
So here's our roadmap. We'll kick things off by defining what a problem-solving agent is. Then we'll dig into the absolutely crucial process of problem formulation. We'll make it concrete with some classic AI puzzles and a detailed route-finding example. After that, we'll look at some surprising real-world applications, and we'll wrap up with the key idea of abstraction that really makes all of this work.
You know, a huge part of being rational is the ability to look ahead, right? It's about setting a goal and then figuring out the steps to get there. This whole process of methodically exploring different sequences of actions to find a path to a solution, well, that's a fundamental technique in AI that we call search.
And that brings us to the star of the show today, the problem-solving agent. This is a specific kind of goal-based agent that is designed to do one thing really well. Find a sequence of actions, a plan, if you will, that takes it from some starting point to a desired goal.
The way these agents operate is actually a pretty straightforward four-step process. First, they formulate a goal. Second, they formulate the problem, which means creating an abstract model of the world. Third, they search within that model to find a solution. And here's the crucial part. Only after a complete solution is found do they move on to step 4, which is actually executing that plan in the real world.
Let's focus in on that second phase, problem formulation, because it is absolutely critical. This is where the agent builds its own simplified blueprint of the problem. It allows the agent to find a solution much more efficiently by basically ignoring all the messy, irrelevant details of the real world.
So to formally define a problem, we need to spell out a few key things. We need to define the state space. That's all the possible situations the agent could be in. We need a specific initial state, where it all begins. We need an actions function, which tells us what moves are possible from any given state. We need a goal test to know when we've succeeded, a path cost to measure how good a solution is, and finally, the solution itself is just a path from the start to a goal. Now let's make that concrete with our Romania route-finding problem. In this case, a state is simply the city the agent is currently in. The initial state is our starting point, Arad. The actions are the roads you can take to nearby cities. The goal test is a simple question, are we in Bucharest yet? The path cost is just the total distance we've driven, and the solution, that's the specific sequence of cities that gets us from Arad to Bucharest.
All right, now let's see how this exact framework gets applied to some classic AI search puzzles. These might seem a little abstract, but they're perfect for understanding how search really works. We'll start with the 4 queens problem.
So the goal here is to place 4 chess queens on a 4x4 board so that none of them can attack each other. The agent starts with an empty board, that's our initial state, and it explores its first action, let's say placing a queen in a corner.
From that starting move, the agent then thinks about all the valid places to put the second queen. As you can see here, this process starts to build out a search tree. The algorithm is smart though. It only expands nodes or states that are valid. It's not going to waste time exploring a branch of the tree where a queen is already being attacked. And it just keeps going, expanding the search tree level by level until, bam, it finds a path that leads to a state where all 4 queens are on the board and nobody's under attack. And that right there is a solution, found simply by searching through this abstract problem space.
The very same logic applies to something like the 8 puzzle. Here, a state is just how the tiles are arranged. An action is moving that blank space up, down, left, or right. The goal test checks if the tiles are in the right order, and the path cost is just the number of moves you've made. And often, with this puzzle, the real challenge is finding the optimal solution, the one with the fewest moves.
Okay, let's circle back to our Romania trip and really walk through how the agent thinks its way through the problem, using everything we've just talked about.
So the agent's job is to get from the initial state, the city of Arad, to the goal state, Bucharest. Now, it's so important to remember this. The agent does all its searching inside its model, the map, to find the entire solution path before it even thinks about starting its car.
So from the starting city of Arad, the agent looks at its available actions. It can drive to Sibiu, Timisoara, or Zerend. The search algorithm will then start building out that search tree, exploring the paths that start from each of those 3 cities, all while keeping a running tally of the total distance, until one of those paths finally hits the goal, Bucharest.
Now, this whole problem-solving framework, it's not just for games and puzzles. This process of formulating a problem and searching for a solution is the engine behind tons of real-world technologies you use every day.
The most obvious one is car navigation. Think about it. An app like Google Maps models the entire world as a giant search problem. The states are locations, the actions are roads, and the cost isn't just distance, it's time, traffic, maybe even tolls. It searches this massive space to find you the best possible route.
It's also used to solve incredibly hard logistical challenges, like the famous traveling salesperson problem. This is what helps companies figure out the most efficient delivery routes, saving them millions in fuel and time.
You know the chips inside your phone? They were literally designed using these exact principles. It's called VLSI layout, and it uses search algorithms to figure out the best way to place millions of tiny components on a silicon chip to get the best performance.
And advanced robotics totally depends on this. For a robot to move across a room, it's not just finding a path on a map. It's searching for a super precise sequence of joint movements and motor commands to move its physical body through our complex 3D world.
Even manufacturing uses this. Search algorithms figure out the most efficient way to assemble complex products. I mean, if you do step C before step B, you might not be able to add part F later on. Search finds the best path from a pile of parts to a fully assembled product.
So how can this one framework work so well across so many different fields, from maps to robotics? Well, it all comes down to a single, incredibly powerful idea. The secret sauce is abstraction. It's the ability to create a model of a problem that just strips away all the junk you don't need, the weather, the traffic report, the color of your car, and focuses only on what actually matters for finding a solution: the states, the actions, and the costs. Without this ability to abstract, the real world would be way too complex to handle. So this process, modeling the world, formulating it as a problem, and then searching for a solution, this is truly a cornerstone of classical AI. It gives us a systematic way to take messy, real-world challenges and turn them into neat, well-defined search problems that a computer can actually solve. And understanding this is absolutely fundamental to grasping how even the most advanced AI systems reason and plan.